तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
In this last part in our series of lectures on computer organization, let us try to take a look at the bus. What is a bus? So far we had seen, right, the blocks of CPU, memory, IO, and then the interconnecting thing as the bus. And on more than one occasion I had pointed out that some kind of standardization we have got to evolve, so that the system from the bus, okay, will see something uniform, all right, because you may be having different types of memory systems and you may be having different types of devices, but the CPU must see something uniform on the bus, at the bus end, fine. Now, in spite of all this, though you talk about some standards, you would find that there are different standards, obviously, right, because the CPU memory, they work at some rate. Then CPU IO, if at all CPU is directly involved, that is going to be at another rate. Then memory IO, that will be at a different rate, and IO by themselves we have a spectrum from the lowest, okay, speed to the fastest one. So, generally you would find that there are different types of buses, and then what you find in the market is a processor comes, okay, with some brand name, and you would find that that particular manufacturer comes with his own bus also. It has happened, and by the time that particular bus gets standardized, you would find that bus is no longer very relevant mainly because the processor is outdated. Okay, this also has happened. Nevertheless, we can always talk in the case of bus in general about specifications of the bus. Okay. Now, here there are certain things which you may find as common, and there are certain things which would keep varying. All right. Now, while specifying a bus, what exactly is a bus? What is it we had talked about earlier? We had always said bus is a set of signal lines. That is what we had said earlier, right. Bus we had introduced as a set of signal lines. In fact, in a very light way, I always used to say, of course, the reason was there for that. The reason is bus in fact is a term introduced by Americans, and earlier the British used to call it as highway. Okay. Now, that particular term is coming in a different context, like super what is it, super highway for information and so on. Okay. Earlier they were calling it as a highway. Essentially on a highway something moves, right. Now, but Americans used bus. Now, in the case of computer system, we can say the bus is like a highway over which data moves, there is some communication. Okay, but Americans called it bus. Why? I do not know, but I used to say, since bus is a set of signal lines, right, these signal lines are carried over what? Rather, these signals are carried over lines which form conductors, right. So, bus has conductors, and bus is usually long, and then while trying to meet the electrical specification, you will find that you would need some current amplifiers. okay, that is we call them as current drivers. So, that means along with the bus or as part of bus you have drivers, right. So, you can see that bus has drivers and conductors, and we are quite familiar with the term bus, right, which way where there are drivers as well as conductors. Good. Now, let us go into certain aspects of these specifications. There are actually 3 types of specifications, but usually in computer organization, or we may say even computer scientists will be concerned more with only one thing. That particular thing is called the logical specification of the bus. In fact, all the time when we were talking about some transfer over the bus, we were indicating this. What did we see earlier? We said the CPU places address on the bus, and if it were a read cycle, the CPU also places a read signal on the bus, right, and then the memory responds with data and it puts it on the bus. CPU of course reads it in. So, you can see that generation of address signal, generation of read signal, and then strobing the data that is available. This is what we were talking about all the time. Now, what is the data? Data is a pattern of ones and zeros, a string of ones and zeros. Similarly, address also, is it not? So, all the time we are only talking about the logical aspect of it, because we never said the data which is 1 means say 5 volts, 0 means say 0 volts or any such thing. That we did not talk about any physical real world quantity. We were not referring to any physical quantity. We are talking about a read as a read signal, write as a write signal. We never said read means okay, what must be the voltage and so on and so forth. So, that is what we are talking about when we talk about the logical specification. And another thing, as you would have noticed, we are talking about a sequence of actions, right? Agreed. Sequence of actions. What are the things we are mentioning? We said first address, then read, and then the data comes which is strobed. So, we are talking about sequence also. So, in other words, the sequence of actions is part of what we refer to as the bus protocol. That is, there is only one specific way in which this read or write can be performed. Okay. So, we talk about logical signals involved, and then we also talk about the sequence in which these signals must be generated. All right. Now, generally when we discuss the bus from in computer science, okay, that or from computer scientist point of view, we will always be concerned with this logical aspect. But related to this, as I was just trying to point out, there are 2 things. One is the electrical specification. So, when we talk about the electrical specification of a bus, then I have got to say, for instance, what does 1 mean? Does 1 and 0 do 1 and 0, do they refer to say some voltage signals or current signals or some other signals, right? And if it is voltage, for instance, what is the level? For instance, 1 and 0, will it be represented by plus 5 volts and 0 volts, or 3 volts plus 3 volts and plus 0.2 volts, or let us say plus 15 volts and minus 15 volts, etc., etc. So, all these things which really refer to the physical quantities, okay. So, they will come under the electrical specification of the bus. Okay. It is not enough if we say okay, the address is placed, we have got to say the address is placed and what exactly are the voltage or current signals, what must be their levels, and also there are other things which we have got to specify. Essentially we can just put it as physical specification, but then when we talk about physical, there is one other aspect, that is why we do not call it physical, because the other aspect of the physical thing is the mechanical specification of the bus also. Okay. So, together these two, they form the physical part of the bus and this forms the logical part of the bus. So, one talks about the electrical signal levels and so on, the other one talks about the mechanical thing what. So, this would say the bus conductor, how long can it be, and the particular bus, okay, what sort of edge connectors are used, is it something like 32 pin or 62 pin, and if it is this pin, is it a parallel or the pins parallel or they staggered, etc., etc., okay, all about this. So, for instance, if we talk about a standard bus, we have specification along all the 3 dimensions. So, if you say multi-bus, there is a specific multi-bus connector, okay, and each of the multi-bus signals is going to be defined in terms of some electrical voltage, current, and so on. And then we also talk about this particular one. So, essentially we will only concentrate on this, but let us not forget that there are these specifications also. Somebody must be concerned with this, otherwise there is no standard. Now, why we must be concerned, for instance, even down to the level of mechanical, mainly because this is the one which is going to give freedom to the user. So, if we say okay, use multi-bus 1 connector or multi-bus 2 connector or some other X bus, new bus, then all he does is he goes to the shop and asks for that connector and then brings it, and then it will have to machine properly without any difficulty. He is not going to be bothered about either logical aspect or electrical aspect. For him, when he keys in, there must be a display, and that particular display, okay, must mean something to him at a higher level. Having said that, we will be concentrating on the logical aspect of this bus. We can note that essentially there are again 3 sections. Okay. The first one we may say is concerned with the data transfer. This is the one we keep talking all the time about. That is, we say that the CPU places address indicates what type of transfer, read or write, input or output, okay, whatever it wants, and then memory or IO response. Okay. So, all these things, the placing the address, placing the appropriate control signal, and then passing on the data, everything will come under this data transfer aspect. Now, as the CPU is involved in this data transfer, because what is going on in any instruction cycle, again and again it is the same thing, fetching an instruction, interpreting, executing, as part of executing, fetching a data, okay, that is instruction or data fetching, it all comes under data transfer. This is what is going on in every instruction cycle. Now, as this goes on, okay, now this is the essential thing as far as the processor is concerned. As this goes on, some other device may indicate that it is ready in the case of interrupt, is it not? Now, in a system which has n number of devices, that is multiple devices, we also said that we have got to look into the priority among this. Okay, when there is a multiple requests for the CPU's attention, so we have to basically see that there is priority checking and so on. So, this particular one we may put it as priority arbitration, okay, meaning as CPU is busy with the transfer, okay, then possibly there is some other specialized hardware unit which looks into the action is priority arbitration, the one which does it is priority arbitrator. Now, priority arbitration is going on in, can go on in parallel with the data transfer. For instance, when so as part of some instruction cycle, okay, when one of the n devices indicates that it is ready, and let us say 2 of the devices, okay, then only there is conflict. 2 of the devices indicate that it is ready. Now, the priority arbitrator will look into their requests and then will choose the higher priority device between those 2 and then say wait, so that when the instruction cycle is complete, it can go ahead. Okay? That is in the case of interrupt. Fine. So, priority arbitration is another piece of action that goes on, and we will have dedicated signal lines as part of the bus. That is what we mean. As part of the bus, you will have dedicated signal lines. Why dedicated? Because then only two things can go on in parallel, otherwise it is not possible. Okay. If the same set of signal lines are going to be used, one has to keep idling. For instance, that was the situation in the case of DMA, right. The IO is directly accessing the memory, so CPU is going out of action. So, fine, that is one thing. And then the third aspect of this bus, we may say, is just put it in general as initialization. Okay. Now, different people may call it differently. What exactly we mean here is something to do with checking about the power, the system clock, and a few other signal lines, okay, which really do not come under, which do not take direct part in data transfer or priority arbitration. There will be another set of signal lines. We may just call them as, for instance, system reset, it is a signal, right. So, that can come under the initialization and a few other things. Good. System clock, system reset, then some special signal lines monitoring the power. So, all these things will come under these. Okay. So, as we talk about the data transfer, we should also take a look at what is going on in this, and also know function of some of these, because this particular thing there is no standard about this. Okay. So, generally when you study any bus, you may be able to identify a group of signals belonging to this or this or this category. Okay. Fine. Now, there are different types of buses, we may say. Actually, I am not talking about for instance, the standard buses here. Okay. I am just trying to give what you may call it as some generic or general classification. Okay. What are the various things involved? For instance, we are not talking about a multi bus or a new bus or a unibus or a mass bus and so on, purely from functional point of view we are discussing. Now, we know that CPU and memory, okay, both work at electronic speed. So, it is meaningful to have a processor memory bus and have it somewhat different, okay, have it distinct from what you may call the second one as an IO bus. Why so? Mainly because in the case of processor memory, the transfer is going to be very fast, whereas in the case of IO bus we do not know. We have devices with varying speeds, characteristics and what not. Then there is one other bus also we talk about, that is generally called a backplane bus. Okay. In some system we may not be able to identify them separately. For instance, the processor memory bus itself may act as a backplane bus. Okay. It is not necessary that all the three must exist in all the systems. Now, let us say someone is rigging up a system with an Intel processor, then suited with that particular Intel, okay, made processor, there may be certain memory chips. It is even possible that the manufacturer of the processor or the CPU has also come up with a set of memory chips which would directly talk, in the sense there will be some special features about that memory thing. For instance, let us say, suppose you have a processor with a multiplexed bus, right, that is, let us say, address and data multiplexed. Then if you have the memory chips, right, or the memory controller which goes with the chip, with the memory bus system, which can take care of this multiplexing, so that internally it buffers and then demultiplexes that, then it is meaningful, no? And so, what happens is this processor memory bus essentially we may say is a short bus, and also it is a bus which does transaction as fast as possible. Fast we can understand, because processor memory for this processor utilization to be the highest, okay, maximal, it must be fast. Okay. And invariably you will even find that the processor and the memory bus, the processor, memory and the bus interconnecting this is processor memory bus on a single board itself. Okay. So, that is why invariably you will find that particular thing as a short bus. And there may not be any standard about this also. For an Intel processor there may be a set of things, for a Motorola processor there may be another set of things. Okay. It is all because of the signals that are generated by the respective processor. We can say that this processor memory bus is a proprietary bus, because we have a specific processor and then we have a specific memory requirement. It is not open for the general use. Now, in the case of IO bus it is a different story, right? Is it not? Number one, we have different types of devices to be connected, okay? And second thing is, whereas in the case of processor memory, even at the time of the design it is known how much of memory and all. At the time of the system installation we do not know how many devices we want, maybe a year after installation we would like to add a few more devices. Okay. So, generally you would find this IO bus is in contrast with the other one. Okay. IO bus will be a long and also slow bus. Slow we can understand, because essentially it is concerned with the IO part, right. Generally it is slower compared with the other one, which is the processor memory bus. Okay. And it is also a long bus, because you may have to have many connectors, right, for expansion of these devices and so on. So, we have a range of speeds to be taken care of in the IO. It is more or less standardized in the processor memory. The user is not directly concerned with this, whereas the user is very much concerned with this, right. And the third one, the backplane bus, what is it? It is on the PC board itself, right. On the PC board itself you have the set of signal lines connected, that is why it even has derived the name backplane. As I said, in some system the backplane bus itself may be the memory processor memory bus. Okay. So, backplane bus we will just see through a few system configurations, okay, the essential difference between these. But take it as the backplane bus is one which you have the entire set of signal lines on the PCB itself, right. So, that is how it has got the name backplane. Fine. Now, regarding the requirements, it so happens there are two requirements about a bus and they seem to be also conflicting. What is that? We talk about generally a bus latency. Now, what is a bus latency? Whenever there is a requirement of the bus for a data transfer, you would like to see that this bus is made available as fast as possible for the specific requirement. Agreed? So, we would have to see that the bus latency time must be minimized. Okay, the time associated with the bus latency must be minimized. That is, whenever there is a request for the bus must be made available with the least delay possible. Then the other factor is the bus bandwidth. Okay. Now, this particular one conveys to us if the bandwidth is high, then more data can be transferred. There is more efficient utilization, okay, is there, that is what we say. Now, when can more data transfer, more data can be transferred? When is more data transfer possible? Obviously, if we can bunch all the data, buffer it and then send it, okay, with the least amount of interaction, asking for address, control and things like that, as we have seen for instance in the DMA, right. The data is ready, is available, and then like a machine gun it keeps going, okay, every time you do not have to keep checking. So, the bus bandwidth can be increased by what we say as buffering the data, okay, and transmitting block of data, okay, so that the time that is generally lost between two say blocks or pieces of data, okay, that can be minimized, right, more. So, buffering, that is holding on, I mean rather storing, okay, more data before the actual transmission starts. So, what exactly we gain here is before the transmission there may be some overheads and delay, okay, but then there should not be any delay once the transmission starts, and once it starts it goes very fast. Okay. Now, buffering and block of transmitting blocks of data, you increase, you maximize the bandwidth. Now, what happens when there is a block data transfer? The bus is not going to be available for some other device which requires, is it not? That is because when the bus is being used by some other device, okay, the one which requests the bus is going to wait, okay, that is the reason. Now, as we said, the latency must be minimized, there is the wait period must be minimized. We also say that the bus bandwidth must be maximized, agreed. Now, while trying to maximize this, we ended up buffering the data and then transmitting the blocks of data, right. And while trying to maximize this, we see that the latency gets affected, is it not? That is, the device which requests the bus has got to wait because some other large transfer is going on, that is the point here. So, these two, bus latency and bus bandwidth, they are actually sort of conflicting requirements. So, there must be some compromise between this, okay. Now, this is very important. Good. Now, talking about different types of buses from the timing point of view, we talk about synchronous buses, okay, synchronous buses in which the transmission takes place, which is synchronized with some clock, and of course, the asynchronous bus. Good. Now, both types of buses are there. Generally, you will find that when synchronous bus is used, everything must be known a priori. For instance, in the case of a processor memory interaction, okay, it is known what is the speed of the processor and then how exactly memory is organized and so on. Whereas, when it comes to IO device, we are not sure. We may add a slow device or a fast device later on also. A priori, we will not know everything. So, it may be better to see that depending on the individual characteristic of the device, the bus transmission must be flexible. Then asynchronous is better. If everything known is a priori, then we can make those elements synchronize, rather work in synchrony, right. That is, for instance, we had talked about, though we did not talk about the bus, we were talking about synchronous action earlier. In what context? I would like you to recall. You remember, right in the initial period, we are talking about states, right, and in each state we are saying some minimum action was going on, right, some minimum action was going on, and then the state itself is being defined by the clock of the system, right, or that is in connection with CPU we are talking about it, remember. Then we are saying in state T1 the address is placed, right, in state T1 the address is placed, let us say the address line may be either 1 or 0. So, either it may be this way or it may be this way. Actually this particular one, okay, refers to rise time and fall time. So, in T1 the address is placed, that is this is the actual address that is placed on the bus, and let us say in T2 the read control signal is generated, okay, the read control signal is generated in T2, the address has been placed, the read control signal is generated, let us say that particular signal is a 0 to 1 going signal, right, that is in T1 address is placed, T2 read control signal is generated. In on seeing the read, the memory responds with the data from where? From the location indicated by the address. So, from now from the memory side, this is all this from the CPU side. Now, the memory, so to indicate that this is different from these, we will call this as the data coming from the memory or memory dot data. Okay. Now, the data is coming when? Sometime after the memory sees the control signal read. So, let us say it that there is some delay. Okay. So, I am just indicating the delay by this delta. Okay. There is some delay from the time the control signal is generated to the time the data is generated. Now, this data actually refers to the data being 0, right. We do not know, maybe some bit is 0, some bit is 1. So, we would represent both. For instance, if the memory responds with an 8 bit data, some bits will be 1, some bits will be 0. Okay. Some bit may continue to be 1, some bit may continue to be 0. So, when we mark like this, it basically it means it can be 1 or 0, right, good. Now, this delta is the delay due to what? Delay due to the memory responding to the control signal read. There can also be delay, okay, introduced by the memory, that is when we talk about reading the data. Delay with reference to the address also is possible, okay. It is not shown here, here only this particular delay is shown, right. Now, here you can see that assuming this delta, that is the delay, is less than 1 clock period, then we say that but before T3 comes this data can be read, okay, is it not? This indicates read control signal and this says data is available, that is we may refer to this as valid data. Why do we say valid data? Because before this instant the data is not valid and during this instant there is some transition. Okay. Now, valid data is available, CPU can actually read any time after this and even before T3. Okay. In this duration CPU can strobe it in, can, but if you want to be very careful you can see that at T3 this information is strobed, meaning let us say something like this, the read control, this edge is used, okay, this edge is used for reading. If that is so, then we say that reading of the data is synchronized with the clock. Now, here this is a clear picture of synchronous transmission. Synchronizing with the T1 clock, address is generated. synchronizing with T2 clock, read control is generated, and in response to the read control, the memory places the data on the bus, and synchronizing with T3 the data is read by the CPU of course. Okay. So, this is a synchronous transmission, which means we know for sure that this delta is not going to be more than this period, that is well before T3 the valid data is available. In case this is not available, we had talked about this situation earlier. In case before the next clock pulse the valid data is not available, that means memory is not responding to this control and address signals. It needs more time, that is what it means. Assuming this particular period is say some 100 nanoseconds and the memory is delaying, let us say by 150 nanoseconds. There is only 50 nanoseconds later the valid data will be available, which means well before the next pulse, that is T4, the data will be available. That is what it means. Okay. So, reading cannot be performed here. So, what will be done? What can be done is the read control signal must be further extended beyond and taken up to T4, is it not? Because the data is not going to be available here, it is going to be available somewhere, we said no, about 50 nanoseconds later. So, the actual valid data will be available here only, not here. That means one clock pulse later, right, it can be read, the data can be read. Good. How is this achieved? What is it? The extension of this read pulse and delaying the reading, how is it achieved? We had seen it earlier. We said that the CPU can have a ready input which can be used by the memory subsystem, and as soon as the memory system sees the read pulse, right, it can immediately say that CPU rather memory is not ready. Okay. Now, on seeing this, what is this ready? The ready is an input to the CPU. On seeing that memory is not ready, then until it becomes ready, for every clock pulse, right, the signals generated by the CPU will get extended. Now, at this point, when the valid data is ready, that is somewhere between T3 and T4, right, when which one? The memory is ready with the data, the memory can pull this up again. So, when T4 comes, it sees that the CPU is ready and reading can be performed right at that point. So, this is how it is done. We had seen this earlier. That is, what we say is this T3, okay, is an extra state that is included as a wait state. That is, the CPU was made to wait during T3, and that was because of the ready input to the CPU, and the ready input is generated by the memory. How and why is it generated? It is known very well that the CPU is fast, memory is slow, that means a priori it is known. So, on seeing ready input which is generated by the CPU as output, ready input to the memory, immediately memory responds saying that it is not going to be ready. And how much to delay is again depending on how many wait states must be introduced, right. Since it is known that more than one state is not necessary, so this will just span for about one state. Now, this is a very clear case of synchronous transmission. The CPU memory makes use of a set of signal lines and the transmission is going on or communication is going on between CPU and memory in very synchronized manner, synchronized with a very clock edge, right. Fine. In the case of IO, we just can't guarantee that. Some buses, some devices may be fast, some devices will be slow, is it not? And it may happen that halfway, okay, through the life cycle of the system, you may bring in some new this one device, right. We may bring in a new device which may be fast or slow, whatever it is. So, in those situations, specifically with reference to IO bus, it is meaningful to have an asynchronous bus, meaning there will be a signal which says okay, start the IO operation, and when the IO has finished with it, it can tell that it has finished its job. If it is a fast device, it is going to tell very fast, the CPU will note it. If it is a slow device, the device is going to take its own time and then inform, right, agreed. So, the master of the bus can initiate data transfer, and the slave, say IO, will take its own time and then it will communicate saying when it has finished the job, okay, that is the transfer. In other words, we can introduce what we may call as some communication between master and slave, okay, in an interlocked manner, master slave communication. Okay. What is this communication? The master says okay, perform this data transfer, and the slave responds to it. So, in an interlocked manner, you establish the protocol of the communication. That is, master says okay, here is the data ready, now you can take it. The slave says okay, I am taking, and this it says taking its own time. Okay. So, we say master slave interlocked communication, and that is what asynchronous is. What is it synchronized with? Nothing. So, it will not go by the clock, it need not go by the clock, clock can very much be there, that does not matter. Okay. Suddenly it is not going to say okay, in this time slot, in this time slot, in this time slot something must be done, that okay, that strict thing is not there. Good. We also say that a set of signals that are used in the interlock communication would be something like say the master and slave, they shake hands. So, we refer to the signals involved in this as handshaking signals. See, you may be able to appreciate why we say this. Say when we meet a person, let us say we say hello, and then he also says hello, and then you shake his hands and say how do you do, and he also says how do you do. It is somewhat like that. Master says hello, are you there? The slave says yes, I am here. Then the master says okay, here is the data. The slave says okay, I have taken the data. So, that means a set of signals involved in this process referred to as handshaking signals, they see to it that the communication goes in an orderly manner, and for a person you see who is not used to speaking very fast, he can take his own time and then say respond with a hello or a how do you do, is it not? Some may be fast, some may be slow, the same situation here too. So, in other words, what we need is a few extra signals somewhat like this. The master may place the address, let us just take a read cycle itself. The master may place the address, and then it may generate another signal which says that the address is placed. Okay. And that signal will be sensed by the slave, and it will respond saying okay, I have sensed there, and it will take the address. Then the master will generate say a read signal, right, and then slave knows that from the address the slave must read and place the data, and after it places the data it says okay, now the data is ready. Now the master will respond saying okay, it will take the valid data that is available on the bus. Some extra signals are introduced, right. So, let us see somewhat like this. The address is placed, okay. I will avoid this bipolar signal, I will just use only one just to show you the sequence. So, let us say something like this. The address is placed, I am just assuming only one this thing. So, at some time edge. Okay. Since we assumed read cycle, let us see that after the address is placed, the read signal is also introduced. Okay. The read signal is also introduced. Now, there are different ways in which we can use a handshake signal. I am just assuming one specific sequence. So, address is placed and read is indicated. Now, from the master point of view, it can indicate that it wants the slave to respond by reading the contents of the location, the address of which is given. So, after it has performed its job, the master indicates, let us say through one handshake signal, we will call it as msync. Okay. So, this in fact is an indication, this is an indication at this time instant master indicates that it wants reading to be performed by the slave, and also gives as already given indication which is the address, fine. Now, on seeing the msync signal, slave understands all this, and in response to this the slave can at this instant, after this instant rather, the slave can respond with the data, that is the memory, the memory, we will assume memory. So, the memory response data, and after this, after whatever delay it is, whatever may be the delay, that delay is because of the memory. After that delay, it generates the data, and this is now available on the bus, valid data. Okay. Let us create some space for the other thing. Now, after the data is placed, the slave, in this case the memory, the slave can generate a similar slave sync signal and indicate that after this instant, it will indicate after sometime after this, that from the point of view of slave it has done its job, that is what it is indicating. Okay. The master indicated by placing address and read, it is an indication to the slave that the slave must perform read. On seeing this master sync, okay, on seeing the master sync, the slave has responded by what? Generating the data and placing it on the bus. After it has done its job, the slave is indicating now this sync is the signal given or generated by the slave. On seeing this sync signal, the master knows that whatever it wants is available on the bus, because after this, okay, after this instant, that is on seeing sync signal, the master knows that the required information is available. Now, the master on seeing this will read, that means this read signal will continue certainly beyond this, and sometime after that it will terminate, right. So, that means by this time the master has read the data. Then after it has read the data, the master may terminate its signal. That is, after this instant when the data has been read, the master will terminate its signal, and on seeing this, okay, on seeing this, the slave may respond with a few things. Let us not worry about that. Suddenly on seeing this m sync going negative, then the s sync also will be pulled down by the slave. Now, this is an indication that the slave knows that master has performed its job of reading. Now, it is closing the whole show. So, we say that there are two handshake signals. One m sync asserted by the master, it is an indication to the slave that it wants something to be done, right, and on doing that particular work, slave asserts this signal, and on seeing the assertion of s sync, m sync, the master, okay, concludes his job of reading and then negates the m sync, and on seeing the negation of m sync, the slave also negates it. So, we see that the signals are asserted, that means the signals placed, and the signals are negated, that is the signals are removed, and you can see the specific sequence. Now, there is absolutely no clock that need be used here. On seeing this signal, the other signal is generated. On seeing the negation of this signal, the other signal is generated, and in between the required activity is done, right. So, this is the way the async bus will work, and you need a set of extra signals for this. These extra signals are something like, okay, like clock, because they really do the timing, but it is not strict clock periods like this. Okay. So, generally these are timing signals. Okay. That is about the synchronization. Now, more about these buses we will see in the next lecture.